Good morning and welcome to this next lecture on sound and structural vibration. Last class we started looking at a structural acoustic waveguide. We derived the relevant equations and we found what we call the coupled dispersion equation. And then I just presented the non-dimensional form. I said I will derive it in this class. Okay, so that is what we are going to see. But before that I would like to present something which I may have done it, but I will do it again because this happens to be the crux of all sound structure interactions. So if we look at the acoustic wave equation, it looks like this: del 2 P by del x square is 1 over c square del 2 P by del t square. It is a wave equation, and we have seen with that crank and spring example that we can represent the pressure using this A e to the power j omega t minus kx. Okay. If we substitute this into the equation above, let us call this 1 maybe. If I substitute 2 into 1, on the left there are two derivatives with space, so I will get A minus jk whole squared e to the power of j omega t minus kx. Okay. And on the right I get 1 over c square, two derivatives with respect to time. So I will get j omega whole squared, then A e to the power of j omega t minus kx. So this we can cancel out A and the propagator. So minus squared is 1, j square is minus, so I get minus k squared, and here again I get minus omega square by c square. So minus can be cancelled, and k now is equal to plus or minus omega by c. The k is the wave number, k is the acoustic wave number, omega is the frequency in radians, c is the speed of sound in the medium. Okay. So plus and minus, because there can be a right going wave with a wave number plus k, there can be a left going wave with a wave number minus k. Okay. So this is with respect to one dimensional sound wave. Okay. And this equation is called the dispersion equation. Wave number given as a function of frequency, okay, is called the dispersion equation. It is called the dispersion equation anywhere. Okay. Sound, 1D sound is very simple. If you look at other systems, it can get very complicated. Next, if we have a 1D plate, as we do in this case, okay, the 1D plate, okay, the equation there is EI del 4W x comma T del x4 plus M mass per unit area del 2 Wx comma T by del T square is equal to 0. This is also a wave bearing system. So, let us say the W of x comma T is given by B e to the power j omega T minus K P for plate x. We substitute this back into, so let us say this is 3, this is 4. If we substitute 4 into 3, I have fourth derivative with space. So, I will get E I minus j k P to the power fourth okay, B e to the power of j this thing omega T minus kpx plus M, and two derivatives with respect to time give me j omega squared, then B e to the power of j the propagator, that is equal to 0. So, B can cancel and this propagator can cancel. Okay. I have EI fourth power of k is equal to m omega square. This is also a dispersion equation. Okay. This is number, let us say 5. So, I have Kp fourth, the wave number in the 1D plate, given by m omega square by EI, or Kp given by this will have 4 roots. Okay. So, let us m omega square by EI, I will have 1/4 plus or minus, and I have plus or minus j m omega square by EI 1/4. Okay. But let us just focus on the positive value here. Let us just, okay, so that is the one we are interested in, m omega square by EI. Okay, while we are at it, why don't I explain the 4 roots and we will. Okay, so let me take the next page. So, we found Kp to be equal to plus or minus m omega square by EI 1/4 and plus or minus I m omega square by EI 1/4. So, let us look at this solution using each of these roots. Okay, using each of the roots. So, I had B, or rather W, given by W of x comma t given by b e to the power of j omega t minus kp is, let us say I take the plus value and I will call it phi. So, phi into x. This represents a rightward travelling wave or a propagating wave, travelling wave. Similarly, if I take the negative root over here, okay, what I will get is b e to the power of j omega t plus phi x, and this represents a left travelling wave, left travelling wave. So, these are travelling waves. If we choose the imaginary roots, okay, imaginary roots, then I have kp, w, let us say I take the positive imaginary, okay. So, b e to the power of j omega t positive imaginary. So, I get minus I phi x. This e to the power j omega t does not bother us, but this j over here, I mean I use j and I interchangeably, okay. So, please do not mind that, I am used to it. Both are square root of minus 1. So, now this j square or I square here, okay, is minus 1. So, this becomes a plus, okay. So, what happens is this becomes b, I will separate it out. So, this would be e to the power of phi x, okay. So, what this means is this is a decaying wave, in the negative x direction. Okay. So, I have this 1D plate over here, suppose I excite it over here, then I will get a positive propagating wave, I will get a negative propagating wave that we have seen above. In addition, I will get a decaying wave on the left hand side. Similarly, if I choose the negative root, okay, if I choose the negative imaginary root, I will get b e to the power of j omega t e to the power minus phi x, and this represents a decaying wave in the positive direction. Those are the 4 roots. Okay. Of these, let us focus currently on this positive propagating wave, which is the positive root here. Let us just focus on that. Okay. Now, if we plot this, if we plot both the wave numbers, so I have this frequency axis, this wave number axis for acoustic wave number and for the plate wave number. The acoustic wave number was omega by c, so it is a straight line, okay, with a slope related to c, it is a straight line. Okay, this is the acoustic wave number. Whereas Kp, the plate wave number, is given by, if I separate omega out, it is square root of omega and 4th root of m by EI. So this is like a parabola, okay. So it goes like this. Okay, and somewhere those two meet. These two cross each other somewhere. That frequency is called coincidence. I have mentioned this before. Or critical frequency. Okay. Now what this means is, if I pick a frequency over here, this is the acoustic wave number. So let us say acoustic wave number is K1 or whatever, at omega 1 it is K1. K1 meaning it is related to a certain lambda 1. So there is, let us say this is the acoustic wavelength. Okay, this is the wavelength of the acoustic wave in the 1D. That means pressure starts with 0, pressure is high over here, this is the acoustic wave, okay. Then again pressure goes to 0 and pressure is low over here. Okay. Now if I take another omega, if I take omega 2 suppose, I am just describing the plot of the dispersion equation, okay, how to read it, because this is a very physical quantity. So at omega 2 my K2 is higher and lambda is inverse of K, so lambda is smaller, okay. So let us say it becomes small. I am not bothering about scales or anything, so just get the feel for the size. Then if I take omega 3 and it is further smaller, so the wave number goes up, wavelength goes down, okay. Similarly with Kp also, the plate wave number. Similarly with the plate wave number, okay. But what happens is, whereas the slope is high, okay, for the plate wave number with respect to omega, initially it's slows down, okay. So that at some point your acoustic wavelength and the structural wavelength, structural plate wavelength are equal, okay. And this is very important because this is when the best coupling can occur, okay, when the acoustic wavelength and the structural wavelength or acoustic wave number and structural wave number are equal, that is when the best coupling can occur, okay. Because here the structure is pulling and the acoustic wave has a low pressure region. Similarly here the structure is pushing upward and by default the sound pressure is high over there, okay, and they match perfectly. So that is coincidence, okay. And it happens because the dispersion equation for the acoustic wave is linear with frequency, and because it's square root of omega dependence in the flexural wave. That's the reason this thing happens, okay. And as you go beyond, the Kp is drops off quickly, whereas the acoustic wave number continues. So Kp here is lower, okay. Beyond coincidence, Kp is lower, which means lambda p remains higher. Sorry. Lambda p remains higher than lambda acoustic, and this condition is important for sound radiation. Now, let us derive an expression for the coincidence frequency omega c. Okay. For the acoustic wave number, k is omega divided by c, the speed of sound, okay, and then kp for the plate is, we will take the positive propagating root m omega square by ei to the power 1/4. So, at coincidence these two are equal, that is what we say, okay. At coincidence these two are equal, that means omega at coincidence by c is equal to m omega square coincidence by ei 1/4. Okay. So, let us take it to match this, let us take this 4 times. So, I have omega c to the power 4th by c to the power 4 is m omega c square by ei, then this cancels to 2, this goes away. So, omega c square is m c 4th by ei, or omega c is c square square root of m by ei. So, it is a material and fluid property. So, if you take the speed of sound c of the fluid, you take the mass per unit area of your plate, you take the stiffness ei, bending stiffness of the plate, they are related and they give omega c. So, depends on both. Okay. Accordingly, let me just write it here, kc, the wave number at coincidence, is omega c by c, and therefore it is equal to 1 c less, c square root of m by ei. Okay. So, I thought I should just repeat this part over here. Okay. So, now typically in structural acoustics, non-dimensionalizations are done with respect to the coincidence frequency. It is a very common practice, either coincidence frequency or coincidence wave number, it is common practice, okay, and it gives physically meaningful results. So, if you have a non-dimensional frequency, you can talk of beyond coincidence, that is beyond 1, or below coincidence less than 1. Okay. So, to remind you, the coupled dispersion equation, the coupled dispersion for the structural acoustic waveguide turned out to be kx to the power 4th, kb or p, I will take p this time, kp to the 4th minus 1. Okay. Kp is the plate wave number, kx is the unknown axial wave number, coupled axial wave number, okay, is equal to minus rho a by, I will put it 0 0 to mean fluid density. Okay. So, rho 0 is fluid density, mean fluid density, not the acoustic perturb density, it is a mean fluid density, okay, divided by m mass per unit area cot kya by kya. Okay. And how are ky and kx related? Ky is equal to square root of k square minus kx square. Okay. So, k is the acoustic wave number in the fluid, kx is the axial direction wave number, okay, and then ky is the vertical wave number. So, at a given frequency k is known, right. At a given frequency automatically k, the total acoustic wave number, is known, whereas now because of the coupling the breakup into kx and ky is unknown. Okay. The two systems are interacting in a coupled manner. Top is rigid, bottom is flexing, and there is a fluid. So, fluid is interacting with the structure, structure is interacting with the fluid, and therefore, the kx is now actually unknown, we have to find that, and kx is related to ky through this. So, we have to find that out. Okay. Anyway, that is the equation. And the non-dimensional parameters, I said omega, the frequency, the non-dimensional frequency I said is going to be omega divided by coincidence. Okay. So, this also means that it is omega by c divided by omega c by c. Omega by c is the acoustic wave number, omega c by c is the coincidence wave number. Okay. So, both are equal, both are the same, apply the same. Then lambda, we have a non-dimensional length which is again coincidence c times a, kc times a, and epsilon, the fluid loading parameter I said is very important, it is the rho 0 fluid density into a divided by again mass per unit area into a, I mean mass per unit area, sorry, both have same unit, numerator denominator. Okay. Then this xi is another which is the one we want, non-dimensionalized with kc. We want kx now, that is our plan. In the whole of this equation, the idea is to figure out kx, okay, and kx is related to ky. So, ky will be replaced in terms of kx. So, that the whole equation has kx, and kx is the only thing unknown, the rest are all known. Okay. So, if we use this non-dimensionalization, what do we get? We get kx fourth by kc fourth divided by kp fourth by kc fourth minus 1 is equal to, I have rho a by m there, so it is straight away minus epsilon, then cot, okay, I will take kc outside, so that I have kc square inside. So, I have k by kc whole squared minus kx by kc whole squared, and I have an a over here divided by, again I take kc, I take kc the denominator inside as squared k by kc whole squared minus kx by kc whole squared and a into a. Okay. So, now kx by kc, this is xi, okay, this is xi we said. So, I have xi to the power fourth, okay, and now what is this kp to the power fourth, what is that thing, kp to the power fourth by Kc to the power fourth. So, Kp to the power fourth is m omega square by EI, as we have seen before, the plate wave number at omega, free plate wave number at omega in vacuum. Okay. And then what is Kc to the power fourth in the denominator? It is C to the power fourth m square EI square. You can check the previous page. Okay. So, now if I cancel off things, what do you get? I get EI cancelled and I get an m cancelled. So, this is omega square EI by mc fourth. Okay. So, this quantity if you again see is my omega c squared. So, what I have here, this entity is omega square by omega c squared, which is my non-dimensional frequency squared. So, this entity in the denominator is non-dimensional frequency omega squared. So, I get here divided by omega square minus a 1. So, let me separate a little. That is equal to minus epsilon cot Kc times A is lambda square root of K by Kc omega square minus xi square by lambda square root of omega square minus xi square. Okay, but it is not over yet. So, I have xi to the power fourth by omega square minus 1. I will bring this up. I will bring this up to the left. So, then I get lambda square root of omega square minus xi square, that is one term. Then the cot, when it comes to the denominator, is tan. This tan I will take it up here. So, this becomes tan of lambda square root of omega square minus xi square. Okay. And then if I bring the epsilon to the left, I get plus epsilon equal to 0. Time has run out for this lecture. I will close it here and we will start looking at how to solve for xi. Okay. Xi was kx in disguise, non-dimensionalized kx. So, we will solve for xi in the next class. Thank you.